This subVI implements the so-called binary symmetric channel, or BSC. The main point of this subVI will be to take a bit stream in, produce a bit stream out, and then insert bit errors according to some bit error rate. Let me begin by creating the front panel controls, which would be the bit stream input as well as the bit error rate. And I'm actually going to illustrate two different techniques. The first one is based on the conventional random number generator. Do a quick help on that, and it says it generates numbers between 0 and 1 with uniform distribution. So each time the VI runs, or if we were to put this inside a loop, it generates a new random value. What we could do is say, well, if the random value is less than our defined bit error rate, then we generate a 1, or generate true as a result of that comparison. Otherwise, we generate a false. So let's just explore this a bit. I'll look both at the random number output as well as the result of our comparison. I'll run this a few different times, and you can see how the random number changes on each run. Now, of course, I need to have a finite bit error rate to see anything interesting on the comparator output. Okay, there's a value where it was higher than 0.5. Here it's lower, and so on. So we can make a fairly ridiculously high bit error rate of 0.9, 1 of course being our maximum value. And so that says the probability of generating an error is 90%. Now what we'd like to be able to do is apply the result of that comparison to the bit stream. Now of course the bit stream is an array, so if we want to process all the values in the array, we need a for loop structure. Wiring the array directly to the left side and using array indexing, which is what that symbol indicates, means that inside the for loop structure we get each individual bit. Now to combine the result of our bit error calculation with the bit itself, we can use the exclusive OR. And that says that anytime anytime we generate a 1 from our comparator, that's going to flip the value of the bit to its opposite value. And if it's been a little while since you thought about exclusive OR gates, you might think back to your digital logic class and look up the truth table for an XOR gate. So I'll label this output with errors and generate another output indicator without errors. Let's just compare these side by side. Let me reorganize my front panel a bit. I'll just put in some arbitrary pattern of effectively 1s and 0s on our bit stream. And I'd like to see how this unfolds on each pass of the loop. So to pace the loop, I'll put in the wait until next millisecond multiple node. 1000 milliseconds is the same as 1 second. Alright, let's take a look at this. Now we can see that most of the time the two indicators are the same. If I raise my bit error rate a bit, we'll see roughly half the time they ought to be different. Now to make it a little more clear where we're at in the loop, let's take a look at the loop index too. Okay, there the errors. When they're the same, that means no bit error was introduced. Now at this point, the thing about pacing the loop so you can watch the details unfold is more just for illustrative purposes. In your finished version, you'd want to take that out. Now to collect all of the results of those computations inside, we simply connect it to the output side of the for loop structure. The default is to use array indexing, so that means all of the internal values on each pass of the loop are collected together into a new array on the output side. So I'm going to take out the loop pacing mechanism at this point. So here we see that the output array deviates considerably from the input bit stream. If I make the bit error rate pretty low, then we see that most of the time it's identical to the input bit stream, but occasionally has an error, as in this point. Again, you'd want to take out those two indicators for your finished subVI application. Now let me turn to a completely different technique for generating the same result. This is based on the built-in subVI called Bernoulli Noise. In fact, the specific type of noise that's meant by Bernoulli Noise, as it indicates here, is an independent set of so-called coin tosses or coin flips, and you can specify the probability of generating a 1. So our 1's probability would be the same thing as our bit error rate. We also need to indicate the total number of samples that we need. Now the intent of our subVI is to simply pipe in the bit stream and then generate the bit stream out. So what we can do is calculate the array size and then have that specify the number of samples that need to be generated. Now the way that we inject the error into the bit stream is still the same mechanism, namely the XOR gate, or exclusive OR gate. But in order for us to work with the result of Bernoulli noise, which is an integer data type, we have to convert that into a Boolean data type. Easiest way to do this is simply compare the integer against 0. If it's non-zero, we generate a true. So what I'm looking at here is simply the results of the Bernoulli noise calculation. Now, as I was saying earlier, we combine the results of Bernoulli noise with our input bit stream, and that generates our finished result. I wanted to point out that one advantage of using the Bernoulli noise subVI is that it accepts what it calls a seed. When the seed is -1, then it generates a different pattern on every run of the VI. If you set this to a positive integer, then every time you run the VI, it always gives you the same pattern. And that can be useful for testing purposes if you want a constant pattern being generated sometimes.